Hello musicians, welcome back. My name is BuckyDurddle and I'm doing another video tutorial on the VCV Rack open source modular synthesis DAW. VCV Rack has many modules that are available for that are open source and some that are not open source. We're covering many of the fantastic open source modules in here in Utopian, and the one today I'm covering is a VCO, a voltage control oscillator, and it's called Dexter. Dexter is by Valley. Now Dexter is a really exciting VCO, and you can see it here on the board up on the rack here. Dexter is not your normal VCO. It's quite complicated. We are used to seeing VCOs that are very simple, single operator VCO, single oscillators, and very simple modules. Dexter is not that. Dexter is very, very complex, should I say. It's a kind of thing that it's like a Swiss Army knife of oscillators. So we're going to have a lot of fun with this. This is going to be a multi-part tutorial. So this first part I'm going to give you, I'm going to be covering a few topics. First of all, the type of oscillator it is and what it's meant to do. We're going to cover the operators. We have 4 operators. Going to cover those and the basic understanding of what they do, and the algorithms and how to get different algorithms in Dexter. So let's get started. First of all, let me go over my little bit of setup here. You can see we have scope running, and scope is connected to X and Y is connected to the. It's hard to see here, but this is the out A and out B. How can I move this so you can see it? There you go. We got the A out left. I'm not going to use the right today. And the B out. So there's 2 outputs on Dexter, and we're using both, and they're both connected to the X and Y in scope. We are also using fundamentals mixer, as you can see right here. And we are also connected, our X and Y, our A and B outputs are also connected to channel 1 and 2 of our mixer, and that's going to our output, which is right here. So that is a very simple setup. Now you can set up Dexter in very complicated ways. It's very cool. And if you go to YouTube, you can find all kinds of great examples of how people use Dexter. You can run it off of all kinds of sequencers and other things, and Bernoulli gate and all kinds of cool things that make really interesting sounds. So, but we're not going to cover that. We are covering the technical of how it actually works. So let's dig in. Now, we are covering today an overview of what it is. First of all, the type of synthesis it does, the operators, and the algorithms. That's the 3 main things we're going to cover today. We're going to cover a few subtopics as well, but those are the 3 main topics. So first of all, Dexter is an oscillator. It's a VCO. But what kind of VCO is it? Well, if we think back to synthesis in the 1980s, there are some keyboards that were iconic at the time. And one in particular was the Yamaha DX7. And the DX7 was offered us FM synthesis and phase modulation synthesis as well. But it did it with a tiny LCD screen. Not only, if you've never tried to program a Yamaha DX7, you probably shouldn't, because it's not a fun thing to do. All of these many variables that's available to you in FM synthesis were available in the DX7, but the interface was this tiny LCD screen. So it made it really difficult to make any adjustments to the parameters. Well, but the synthesis was sound. And many of the keyboards at the time had the same problems, where it was so complicated, the synthesis was so complicated, it was hard to find an interface that really would allow people to use it. So Dexter gives us what the Yamaha DX7 was giving us in the 1980s. It gives us the ability to work with frequency modulation, FM synthesis, and phase modulation synthesis. So both of those are incorporated in here. Now that is what it does. Now this tutorial today is not about frequency modulation synthesis or phase modulation synthesis. This is about Dexter and the getting you started. So I'm not going to delve into that yet. I may in a future tutorial, but I want to get you going on how this actually works. And we'll get into the actual synthesis a little later when we look at the wave tables and we look at how they are manipulated using the different operators, but not today. So on Dexter, we're given 4 operators. And you can think of operators as the same as oscillators. Like if we went to fundamentals here and pulled up a VCO 1, this guy here, this is an oscillator, and could be called an operator. And it would give us all kinds of parameters. Of course, we've seen this before because I've used this oscillator many times in the tutorials. The VCO 1 is an oscillator, just as Dexter is an oscillator. Dexter gives us many, many, many more things within each operator, so it's very, very handy and very dynamic. We can do a lot of things with it. So let's just go over a couple of things here with the operators. So these operators, they each have parameters, as you can see, and some of these parameters you may recognize. Now, I'm not going to go over all the parameters of the operators today because this will come into future tutorials, but I want to give you a couple of little pointers here. First of all, if we look at, we'll take operator 1. I'm going to turn my volume up a little, and so you can hear we have a sine wave going on, which you can see here on the scope. Now, if I adjust my level, you can see the sine wave will decrease, and the wave itself, if I change this, you can see that this will manipulate the wave. And you may recognize some of these shapes that we're seeing here that we've gone over in other tutorials. We see some folding happening. We see square wave, saw wave. We saw a triangle earlier. So we see all kinds of little inversions and things like that, and unipolar and bipolar waves. The full sweep over the waves, over the wave knob here, the dial, just in this original setting, the default setting, gives you a lot of options. Okay, so that's the wave. The shape is much like a pulse width. You can see it's moving the wave together. Now let me just move over to a saw shape on the wave. It should be there, and now you'll see the pulse width. You see it acts like a pulse width. Now if I go over to saw, or a variation on saw, and I do the same thing with my shape, you can see it does a variation pulse width. It's not an identical pulse width on all these waves. Every wave responds to that control a little different. So you can see, you get some really interesting shapes and sounds. So that's our wave and shape. Now, in the default setting, that's what it does. But we have the ability to change the wave that we're hearing. You have the ability to change that. And you can do that by changing, if we go up here to this little selector up here, this gives us a little preference for this one oscillator, this one operator. And there are a lot of things here, but I'm not going to go over all these in this tutorial, but I do want to show you this table. This is our wave table. We can choose different wave forms we want to use. And you can see in our scope, we're getting all kinds of variations. Now I'm going to go back to Opal at the beginning. As I go up through, you may recognize some of these names. We've got oboe, sax, cello, violin. So these are sounds, these are waves that have been designed to try to emulate certain acoustic sounds. And they're not all, of course, because we see some there that are really strange, like, sine, harm for harmonic. Harmonics, add, saw. We go all the way over here, video game. So this one here is meant to emulate various video game sounds that were in these video games. And voices. And if you like this one, the voice sounds, you can look at my tutorial on. You can look at my tutorial on Vox Inhumana, which was a really great formant module, which gives great vocal sounds. But I digress. So you can change your wave shape here. And when you change it here, I'll change it to say, let's say leave it on cello. If I close my little window now if I change my wave shape, see it's giving us, it makes the wave shape change, but based on that wavetable waveform that we've chosen. And of course the shape here as well. Make sure I use these words right, because this is the wave, not the shape. This is our wave dial, and this is our shape dial. Shape is very much like a pulse wave. Okay, so I'm going to turn my volume down a little bit on this one, and we'll continue on. I'm going to initialize the module now, just to take us back to the default. So that is the first operator. Now, let's talk about the second operator. But before I talk about the second operator, I got to talk to you a little bit about what's going on here. What's happening in FM synthesis is one operator has the ability to affect another operator. So I'm not going to get into the fine details of what happens, just to say that the sound is changed by what the next operator along the chain is doing. Now, before I get into operator 2, let's have a look over here at algorithm, this algorithm section right here. Now, I'm not going to change this now, but I just want to show you this. This is a line of how the sound would be coming along to come out through our A and B outs. This is our A and B right here. And the operator number 1 is on. So I'll turn my volume up a little again. Operator 1 is on. Operator 2 is not on yet. See the level? This is the level right here and level right here. Operator 2 is off. But if I turn it up, you can hear and you can see on scope that that sound is being changed as I introduce a new waveform, a new sound from operator 2. It's now changing the overall sound, the sound that's coming out of the A and B out. So if I just up this a little bit and I change my wave shape, we're getting new sounds. And if I change my shape, so you can see that by changing the dials here on wave and shape and level, I'm changing what's coming out of A and B, and so operator 2 is now having a direct effect on what operator 1 is doing. Also, one other thing I didn't mention earlier is we also have a coarse. This is frequency. Like on all oscillators, we can do coarse, we can also do fine. That's just frequency changes. But the reason why I mention that right now is because now if I bring up my level a little bit on number 2 and I introduce a tiny bit of frequency change, you can hear what it does to it. You can introduce all kinds of interesting sounds by playing with these options. Now, right now I want to point out I have operator number 2 turned down. It's off. Okay, operator 2 is off. Operator 1 is on. If I turn operator 3 up, nothing happens. Operator number 4, nothing happens. And the reason why nothing is happening is because it happens in a chain. If number 2 is down, operator number 3 affects number 2. Operator 2 affects number 1. So it goes in a chain. And you can see over in our algorithm, it goes 4, 3, 2, 1. It goes in an order. So if number 2 is turned down, number 3 it doesn't do anything. And number 4 does nothing as well. But if I turn up number 2, now I turn up number 3, you see the change. If I turn up number 4 now, you see so all 4 operators are now affecting the sound. Number 4 is changing number 3, 3 is changing 2, 2 is changing 1, and 1, they're all going out through A and B. And again, down the bottom here, you can see A and B out right there. They're both coming out through. The sound is all coming, the same sound's coming through A and B. Okay, so that's operator 1, 2, 3, and 4. Now, let me just show you something too. I have my number 1, operator 1 is up. I'll turn up operator 2 a little bit. Okay, now if I go up to my pull down parameters and my preferences for that one operator, I can again change my wavetable here. Now, the sound that I choose for operator 2 is affecting operator 1 in a different way because I'm not using Opal, the original sine wave. I'm not using that anymore. I'm using a different sound. So now you can see, and you You can see on scope, and you can hear in your sound. It's a very different sound. And now, even if I play with my fine tune, you can see there's a lot of very interesting sounds we can get with this. So I'm going to initialize operator 2. So there you go. Operator 2 is back. I'm going to put it back to where it was. Now it's back on opal, which is a sine wave. And again, if I turn up my level, it's just a sine wave again. Okay, so again, we can set each individual operator to have its own wavetable sound, whichever one we want to have. And we can, again, fine-tune these with our wave and our shape. Operator 1, 2, 3, and 4, each can be different. You fine-tune this, you're going to find very, very, I'm going to say unique. It will be very unique. It will be unique. You'll be able to create unique sounds. Okay, now let's move on to our algorithm. But before we get on to algorithm, I'm going to turn my volume down, and I have to speak to you a little bit about our outs. Okay, now, as I said earlier, this is the out of A. It's left and right. It says A is stereo, but I'm only using the left channel. This is A, and this is the B out. And we know that through our algorithm, operator 1, 2, 3, and 4 all go out to A and B. But when I dial my algorithm, it changed. See that? It changed. So what happens here in this algorithm is different than the first one. Let's go back to the first one. First one, it goes in a chain. 4, 3, 2, 1, output. If I go up one notch, 3 and 4, they work independently. They're not affecting each other. But then both together as a sum affect 2. So it'll give us a different sound. So let's just see what that sounds like. Now let's make I got this set up here now. So we're going to get a unique sound. It's not the prettiest sound in the world. But now you'll see, if I switch to the next algorithm, so in the first algorithm, it's going, what's happening in number 4 affects number 3, and that together affects 2, and that together affects 1, and then comes out the output. And I go to the next algorithm. 4 and 3 work independently, but as a sum, they both affect 2 equally, and then 1, and then out the door to the output. So it gives us a different sound. So we can fine-tune this sound. We can fine-tune our sound by changing different algorithms. So let's have a look at some of the other algorithms. Next one. So here you go. 3 is the top of the scale. Then it goes to 2. And then what comes out of 2, 4 is combined with 2, and that goes to 1. Again, different version. And look, there's another variation on that. And then there's another variation, and another, and another. It goes on and on and on. And you can see the way let's turn our volume up a little bit and hear what that sounds like. You see, some of these are very different, very interesting too. And some of these, like with this one right here that we have now, let's look at the algorithm. Number 4 is going by itself to the A output. So number 4 is, if I turn my B off, I'll turn my B input off. That's the A. That's 4. So if I adjust my volume, you can see that's 4. It's only 4. But if I turn my B back up, that is 1, 2, and 3 equally coming out as a sum coming out. So all these sounds are all, the sound that's coming out of B is a combination of 1, 2, and 3 all coming out equally. So you can see that all of this, that these algorithms give us all kinds of different interesting ways. Oh, that's loud. Here we go. So the algorithm gives us all kinds of different ways that we can take operators and have each operator affect the next operator in a different way. Very, very interesting stuff. So in frequency modulation and phase modulation that we're going to be working on here, this is really interesting, really full of possibilities for us. So let's just do a quick little review here now. We learned, of course, that this is a phase modulation synthesis, FM, and it's also, a frequency modulation synthesis, FM, and phase modulation synthesis, which is PM. But the phase modulation and frequency modulation synthesis is possible within this module. We also learned that, that's similar to what was done in the 80s with the DX7 and other keyboards as well. There's also a lot of wavetable synthesis in this. You've heard me talk about wavetable, and some of the wavetables things that are available to us in Dexter is still used today in many synthesizers. We have 4 operators, 1, 2, 3, 4, and these operators have a lot of different possibilities in how we can use them. We're only just beginning to scratch the surface on what these can do, and there's a lot of buttons and things here I didn't even talk about today. So these 4 operators, they are the heart of our synthesis in this module. And these 4 operators, they output the A and B, but how A and B is organized and how these synthesizers modulate each other and affect each other, it depends on our algorithm that we choose right here. And the algorithm will out to A and B in various different ways. So you can choose. You have a wide variety of different algorithms you can use here for that. And that is basically Dexter. And that's the introduction to Dexter. I'm going to do a number of tutorials on Dexter to try to dig into some of the exciting things that we can accomplish with this synth. So I hope you come for more. You stick around for more tutorials. We'll be playing with Dexter for quite a while. This is a beautiful module. And again, it's by Valley. And Valley is, you can see the GitHub repository in the post that I have here. Be sure to go to the developers' GitHub repository and their webpage and show your support for them. They're doing some great work. I'd like to see more support for these fantastic developers who are doing some great stuff for us out in the music community. So thank you very much for joining me today and exploring the Dexter modular synthesis synthesizer. I really appreciate your time, and if you have any questions, feel free to connect with me on the utopian.io Discord, and you can also leave messages for me here in the comments of this post. Thank you very much for watching, and I will be seeing you next time.